Lesson 2 Review, Basic Instruments and Measurements. This lesson covers the basic instrument meters we use to measure various components in the electronics field. You will change and grow in the field of electronics, but the basic usage of these meters will not. They will only vary in type and their ability to do multiple readings without changing meters. These meters come in two formats: analog, figure 2.1, and digital, figure 2.2. An analog meter is a meter in which the scale has a continuous value. The common type of analog meter is used to measure voltage and current. This meter uses what we call the Dasserval or iron vein movement to produce a reading. Dasserval is accomplished by taking a moving coil with a needle attached and sending current through it to produce a magnetic field, figure 2.3. The magnetic field interacts with the stationary field and causes the needle to move. The needle movement is proportional to the amount of current flow. If current increases, the needle indication will be greater. The opposite occurs when the current decreases. It is imperative that the leads the current passes through are connected properly to prevent a false reading. Most meter connections will have slots for two leads, a black for negative, sometimes labeled common, and a red for positive. Iron vein is accomplished by placing two pieces of iron inside of a coil of wire that is induced with current which magnetizes them. Because both pieces are magnetized with the same polarity, they will repel. One will become stationary and the other will be pivotal. The pivotal one will have a needle attached which will move to the left or right depending on the current or applied voltage. See figure 2.4. In this type of meter, movements, current and voltage can be read in either AC or DC form. With iron vein, when used to check for voltage, the coil is wound with many turns of fine wire and a resistance multiplier with a selector switch is used to increase the range. When it is used as an ammeter, the coil will be a few turns of heavy wire. The reason for this is that when reading current, the meter must be hooked in series with the component you are trying to read. Let's talk a little bit about the meter scale used to interpret the voltage and or current in the previously discussed meter movement. The scale is evenly spaced apart with numbers to indicate the voltage or current it is reading. It is known as a linear meter scale, figure 2.5. Looking at the scale in figure 2.5, the greatest number on right is 1. The smallest number on your left is 0. This makes the scale range of 0 to 1. Because it is a milliammeter, it is 0 to 1 MA,
or milliamps.
The small lines in between the tall lines are in 0.05 increments. The tall dark lines are read in increments of 0.2. Therefore, when you reach a tall dark line, you add 0.2. For example, if the needle is past the 0.6 line and resting on the second small line after it, it is reading 0.7 milliamps. When you add a selector switch to this meter, it will be used to change the range from 1 milliamps to the desired number range of the switch, and the line increments will change. There are many different types of meters used to read various readings and levels in the electronics world. Let's take a few minutes to cover some of the more important meters we use on a regular basis. The first meter we will discuss is the ammeter. An ammeter is used to read current in an electrical circuit. It is read in amps, milliamps, and microamps, depending on the scale. Most meters will have a shunt resistor, which provides an alternate path for current to flow so the meter can read high levels of current, figure 2.6. As I mentioned earlier in this lesson, in order to read, it must be wired or connected in series with the system you're trying to read. This is done by breaking or opening the line and placing one side of your meter to the component line and the other side to the open line or the battery, figure 2-7. The next type of meter we will talk about is a voltage meter tester, figure 2-8. A voltage meter is used to read voltage levels in a circuit. This meter will usually come with the capabilities of reading both AC and DC voltage levels. The voltage meter is the most important meter used in our field. The meter can give you the indication levels which will tell you if the equipment and or the technician's life is in danger. Checking for voltage tells the technician whether the equipment is live or energized. The voltage meter uses a resistor in series with the meter movement coil to allow for high reading. The resistor is controlled by a switching device which changes the range level readings of the meter. Voltage meters are always connected in parallel with the component or device they are trying to read, figure 2.9. A general rule of thumb is to always set the selector switch to the highest range when reading unknown voltage. Meters cannot read AC without help because AC is constantly changing. To accommodate the change and allow meters to read AC, a rectifier is installed to convert AC to DC. It merely rectifies the current to an equal DC value. This is called root mean square, or RMS. Ohm meters, figure 2.10, are used to measure the resistive value of a circuit or component. This meter is like the voltage and current, and in that it uses a resistor in series with the coil, but it reduces the voltage to the meter coil. It uses a selector switch to control the variations, which allows greater values to be read on the meter. This meter must be zeroed in order to get an accurate reading. This is done by turning it on and touching the two leads together for a zero reading. The highest value on the meter is identified by the infinite symbol. This meter is unique from the current and voltage meter. For this meter to read resistance in a circuit or across a component, power must be removed. This is what we call cold checks on a circuit. Failing to de-energize a circuit before performing resistance checks can cause harm to the meter and to you. I have described 3 of the highly used meters in our field, but there is also a meter that is capable of performing the functions of all 3 of those meters. This meter is called a volt-ohm-milliamp meter, or VOM, figure 2.11. The advantage of the VOM is its low price and durability. Although this meter can be found in analog or digital, figure 2.12, digital is by far the most widely used in the electricity and electronics field. These meters use a combination of electronic circuitry for measurement. The liquid crystal display screen that displays the values and the accuracy of the VOM is highly favorable with technicians.
The price and type of meter
varies depending on the type and manufacturer, whether it can read AC or DC voltage, AC or DC current, resistance, frequency, capacitance, diodes, and whether it can be used as an oscilloscope. Those are just some of the capabilities a digital multimeter can perform for you. The basic operation of most multimeters is very simple and will always apply across the board. The first step is to place the black lead in the black slot and the red lead in the red slot. If it is the type of multimeter that can be used for more than just voltage, current, and resistance, a brief look at the owner's manual is recommended. You will merely move your leads from different slots before taking a reading. The selector switch is used to vary between the types of readings you will take: current, voltage, resistance. Remember that when taking current readings, the meter has to be placed in series with the component you are trying to read. Resistance readings are taken while the power is de-energized. Voltage readings are taken in parallel while the power is on. Just the thought of taking voltage readings on live electrical or electronic circuits makes performing your job very dangerous. All safety precautions and understanding preventing electrical shock is mandatory. Electrical shock occurs when the current passes through the human to ground. If you touch an energized circuit, you can serve as a path for ground. The voltage level is not what is the most dangerous. It is the amount of current that passes through your body, which can kill you. Figure 2.14. Don't misunderstand what I'm saying here. The voltage has an effect because the higher the voltage level you are working on, the higher the potential of current that is available for the circuit. One way to reduce the amount of current that can pass through your body is by keeping your body resistance up. The formula for current is current equals voltage divided resistance. The more you sweat, the lower your body's resistance. One of the best ways to prevent shock is to learn how to work with one hand in high voltage conditions. With one hand in your pocket, you don't provide a complete path for current to flow through you, that is, through your heart from arm to arm. All electrical systems should have a safe path for ground. The ground symbol is shown in figure 2.14. A ground connection provides a path for electrical faults and has 0 volts. Grounding is accomplished by connecting a wire from one of the electrical systems to the earth or metal casing, figure 2.16. The National Electric Code, NEC, requires that all electrical and electronic systems over 50 volts be grounded. The NEC is the governing body that sets all the standards for safe installation of electricity equipment in the United States. Ground fault interrupters, figure 2.17, were created in order to help combat excessive current faults, which lead to shock. They provide protection by monitoring and comparing the current in wires. If the current exceeds 5 milliamps, the coil will be tripped and the circuit will be de-energized. You will definitely see ground fault circuit interrupters in areas where you use water, like the bathroom, kitchen, and outside receptacles. Each ground fault will come with some type of schematics on how to wire it up. A schematic diagram will provide illustrations of the circuit, showing how it relates and connects to other components. Symbols are used to represent components and lines are used to represent wires and conductors. The ground fault, which can be line, wiring, or block, is the most important tool for troubleshooting electrical and electronic equipment. The lines show the system electrical controls, how the system electrical controls communicate to others in figure 2.18. The wiring illustrates the position of the connection points and components in the equipment, figure 2.19. As we continue to move through the lesson, the symbols used in the electronics field will begin to become clearer and easier for you to identify. A list of some of the different symbols you will come across are displayed in figure 2.21. I don't expect you to memorize them, but try to get acquainted with them as you go. Most schematics will give you a brief breakdown of the symbols. I want to finish this lesson by saying, as you may know by now, that working with electricity can be very hazardous, and knowing the proper first aid response to a shock victim can save their life as well as your own. The immediate steps are as follows. Call for help, ensure power is off, and ensure the victim is not still in contact with the live wires or the circuit. If they are, try to move them from the circuit
with a non-conductive item,
like a piece of wood, plastic, or an item of clothing, without touching them yourself. Once you know for sure that they are not in contact with a live circuit, check for a pulse. I'm not going to go into cardiopulmonary resuscitation, CPR, because I'm not qualified to teach it. But there is a section in your textbook that will go over the basics of CPR. Most employers will require and provide you with CPR training on a regular basis. I will tell you from my experience, when working on energized electrical systems, if possible, always use the two-man rule. If another technician is not available to assist you, be sure to inform some other personnel that you will be working on the equipment while it is energized. On the text, there are a few websites to help you with this lesson, and remember that I'm just an email away.
Review questions. Electricity and Electronics, 10th edition by Garish and others. Chapter 2. All sections in review and test your knowledge questions are included. Content, of course, is by the authors of the textbook. Answers, narrations, and explanations by Hector Vladimir. Another name for a stationary magnet moving coil is the arson ball movement. Explain how a moving coil meter operates. When a current passes through a moving coil, a magnetic field is produced. This field reacts with the stationary field and causes rotation or deflection of the needle. You must be careful when handling a moving coil. Why? Because it could be damaged by impact. A linear meter scale has blank spaced marks to indicate circuit values. It has equally marked spaces. An ammeter is used to measure current. In order to measure higher current, A or N blank or alternate path is provided for current. Fill in the blank. A shunt is used to provide for an alternate path. An ammeter should always be connected in blank with load in series. An ohm meter is used to measure what?
Resistance.
An ohm meter uses A or N blank scale, a nonlinear scale. An ammeter uses a blank scale, linear scale. Again, an ammeter measures
Amperage
or current. Why must you calibrate a ohm meter before use? For accuracy. Find the value of the multiplier resistor Rm shown on the figure on the right side. It should read 50 volts across points A and B. For this problem, we use the formula R for resistance, M for multiplier, equals E over I, or E divided I. If this formula looks familiar, it's because it is familiar. It should be, at least. It is a form of the Ohm's law. So resistance multiplier equals, in this case, 49.9 over 0.001. Again, we put for the voltage 49.9. Why? Because there are 50 volts being read across points A and B. And since on a multiplier resistor,
specifically
for a voltmeter, no more than 0.1 volts is required to deflect the needle, the movement, all the way to top off, or all the way to the number 1, which is from 0 to 1, 0 to 10, 0 to 20. In this case, it's 0 to 20, so it'd be topped off at 20, which would be equivalent to the 200 mark. So you take off the 0.1 volts from 50 volts, which gives you 49.9. Remember, we're looking for the resistance of Rm, or resistor multiplier, shown in the figure. So for that, we use a form of the Ohm's formula, or Ohm's law equation. We substituted its values, 49.9 again, divided by 0.001, and where the 0.001 comes from is the amount of current that requires full deflection. So you put that there in place of I current. Divide that, you get 49,000 ohms for the resistor value. So a 49,000 ohm or 4K ohm resistor will give you a reading of 0 to 50 volts across points A and B. Again, if it's 50 volts, it'll give you full deflection. If it's somewhere in between, it will give you less than full deflection. What does the abbreviation COM or COM stand for on a meter? What is its polarity? The common is what this COM means, and its polarity is negative. The common is more often used in AC circuits. What does DMM
stand for? Digital multimeter.
How should you connect an ammeter to a circuit? In series with a load by first opening up or breaking up the circuit. Which of the three main types of meters should never be used when the circuit is energized? An ohm meter. What is an electrical schematic? A technical drawing or diagram showing parts of the circuit and how they connect to each other. What are electrical symbols used for? To represent different circuit components and their functions.
Name.
Electrical drawings and the use of each. The first is block diagram, which shows the flow and how the overall system works. The second is elementary wiring diagram, clearly expresses how the system works. And the third is wiring diagram, which is an aid to install or troubleshoot the system. The Arsenval movement measures blank and blank. It measures voltage and current. A or an blank is an alternate path supplied for measuring large current. It is a shunt. An ammeter movement has a moving coil resistance of 50 ohms and requires 0.001 amperes for full scale deflection. Compute the shunt values for the ammeter to read the following ranges: 0 to 1 milliamp, 0 to 10 milliamp, and 0 to 50 milliamp. First, find the voltage for full-scale deflection. Since we have already the ohms available and the amperes required for full-scale deflection, we can compute the voltage for full-scale deflection using Ohm's law. Voltage equals to 0.001 times 50, which is 50 ohms, which is 0.05. Breaking down the different settings, 0.01 and 0 to 1 milliamp, the first set of answers. We set up a version of the Ohm's law equation as R resistance S1 equal to voltage over or divided current. R1 is the shunt resistor value, and we get 0.05 divided 0.001. Again, we get 0.001 from 1 milliamp from the setting that we want to solve for. In this case, 0 to 1 milliamp. So resistor S1 equals to 50 ohms. And as we can see in the drawing, since the meter coil has already a 50 ohm resistor, there is no need for the resistor at position RS1. That one will do just fine to get us what we need, which is a amperage measurement of 0 to 1 milliamp. Next setting, we solve for resistor S2 equals to voltage over current or divided current, which plugging in the values again, 0.05 for the voltage divided 0.010, which again comes from your 10 milliamp setting, 0 to 10 milliamp, 0.010
amps.
That gives us 5 ohms. Solving for your third setting, 0 to 50 milliamps, RS3 equals to power over current. We can plug in 0.05 again, divided by 0.100, which is the setting of 0.50. So 0.05 divided 0.050, which is 50 milliamps. 0.05 divided 0.050 amps equals 1 ohm. The answer for the third setting, 0 to 50 milliamps, is 1 ohm resistor for position RS3. In this problem, we compute the multiplier resistors for the voltmeter in figure to use the following ranges. Again, looking at the problem, we want to compute for multiplier resistors of a voltmeter. Very important to differentiate between an ammeter and a voltmeter when working out problems. Also, notice the difference in the figures, the way the resistors are set up. They are starkly different between an ammeter and a voltmeter. The ranges that we're going to be solving for is 0 to 1 volt, 0 to 10 volts, and 0 to 100 volts. Some conditions: 1. The moving coil resistance is a 50 ohm resistor. 2. The meter allows only 0.001 amps or 1 milliamp full scale deflection. And 3. 0.05 volts is allowed across the meter. No more than that. We get 0.05 volts from 0.001 amps times 50 ohms equals to 0.05 volts. Solving for the first setting, 0 to 1 volts. For the voltmeter, we get what looks like a Ohm's equation in a different form, again with the resistor on the left side. Solving for the resistor, Rm1 equals to voltage divided current. Again, this is the multiplier resistor for a voltmeter. We get 0.95 divided by 0.001. 0.95, why? Because 0.05 volts is allowed through the meter, right? So if we want to get up to 1 volt, so 1 volt minus 0.05 equals to 0.95. So we want to allow only 1 volt, so we use 0.95 volts in this formula to get the size of resistor, RM1. That's the size of resistor we want to basically resist 0.95
volts
out of 1 volt and allow 0.05 volts through. So if we want to resist 0.95, we have to know what RM1 is by using 0.95 as your voltage. And you divide 0.95 volts by 0.001 amps, which is the allowable amount of current in this case, as given in condition number 2. Again, another explanation of 1 volt, we must resist 0.95 to meet condition 3. So RM1 equals to 950 when you divide that. And that is 950 ohms. Next setting, 0 to 10 volts. Resistor M2 equals to voltage over current. In this case, the voltage is 9.95. Again, we want to allow 0.05 volts through, so 10 volts, which is the maximum. In this setting, we take 0.05 away, we are left with 9.95. We divide that by 0.001, which is your maximum allowable current, and that gives us 9,950 ohms, or 9.95k ohms. The third setting, 0 to 100 volts for the meter. We want to find resistor M3, the value for it, to give us what we want, which is a reading of 0 to 100 volts. We plug in 9.95 for voltage. Again, we want to allow 0.05 volts, the same as the other two settings, 0.05 volts. If we take away 0.05 volts from 100, we're left with 99.95 volts. And you divide that by your maximum allowable current, 0.01 again. That gives us a resistance of 99,950 ohms, or 99.95k ohms. A meter is used to measure the value of an unknown resistance, and that is called a ohm meter. The symbol on an ohm meter scale represents watts. That is the infinity symbol, the mathematical infinity symbol, and it's a representation of watts in your ohm meter. It represents high resistance or
infinite resistance.
When reading an unknown voltage value, you should set your selector position to watts. Again, your voltage is from a voltmeter. If you don't know what the value is, what you're reading, you should select it to the highest possible voltage range setting. When using the ammeter, you should connect it in what kind of way with the load in series. You want to open up the circuit and basically insert the meter as part of the circuit. What type of meter must be zeroed out? The ohm meter. What is meant by loading the circuits? This term is a bit more loaded than it looks, a bit more involved. However, they're not too complicated. There are a few steps that you may want to consider and perhaps practice to get a better idea of what loading the circuits is. To define loading the circuits is when a voltmeter is connected across a resistor. In parallel with it, it loads the circuits due to the shunt resistors in the meter, causing a shunting effect, in fact an error, in voltage drop across the resistor. So basically, testing for a voltage drop across a resistor, which you have to connect your meter in parallel with the resistor. Let's say on a 2 resistor circuit, as the example in figure 2-11. When you load the circuits with your meter by testing this 1 resistor out of the 2, the shunting effect of your meter, basically the resistors in your meter, introduce an error in voltage drop across the resistor. That is, if your meter is not of high resolution or a very high quality, you can actually introduce an error reading that voltage drop, and it'll give you a voltage drop that is different from what you would get if you were to work the theoretical voltage drop, say with Ohm's law equation. And to show you how that is worked out, how we find out about that and why this actually is, why this happened, we have to define again a few things. The effective resistance is the total resistance read by your meter. Not necessarily the actual resistance of the resistor, it is the resistance read by your meter. Your
effective resistance
in formula is R1 or resistor 1
added to
your resistor multiplier or the resistor from your meter, which is your resistance at your meter, that is Rm, and then divided by 2 as shown. So in this case, we have a resistor 1 value
of 10,000.
If you look at the diagram, we have a Rm value
of 10,000.
That is your resistance at your meter
of 10,000.
However, we plug in
different values.
We plug in half of those. Resistor 1 and Rm values are decreased by half. The voltage divided you actually create when you plug in your meter leads into the
circuit
across resistor 1. So you actually have to use half of the values of R1 and Rm. Instead of 10,000, you put 5,000 ohms plus 5,000 ohms. Again for R1 and Rm. You divide the total for that addition, 10,000 divided by 2, and you get 5,000 ohms. So with the meter connected, the total circuit resistance becomes R effective plus R2. Again, R effective or resistance effective is your combined meter plus resistor 1 divided 2 reading. So it's a composite
Resistance reading.
and you add that to the second resistor, R2, which gives you your R total, resistance total, which in this case is
5,000 ohms plus 10,000 ohms equals 15,000 ohms.
so your resistance total is
15,000 ohms. Then to get
your total current. If you haven't gone through this lesson yet, your total current is the same at any point in a series circuit. So we must get value by again using Ohm's law. Current total equals to voltage divided resistance total or R total. Current total equals to 10 volts at your power source in this circuit. Figure 2-11, 10 volts divided 15,000 ohms. 15,000 again is your resistance total. Current total equals, when you divide, 0.00066
amps.
To get your
Voltage for
your resistor number 1, you
get
your resistance, your current total multiplied by resistance total, again Ohm's law, that gives you 0.00066 multiplied by 5,000 ohms. Again, we're looking for the voltage drop R1, resistor 1. 0.00066 times 5,000 equals 3.5 volts. That is your voltage drop at resistor 1. That is your actual voltage reading at your voltmeter at the R1 when you measure across it. And this is an erroneous reading. You should be 5 volts or somewhere near 5 volts because you have a 10,000 ohm resistor and you have 10 volts. So you should get 5 volts at each resistor. Again, power or voltage across a 2 resistor circuit in series should divide equally. In the 2 resistors, you'll find out about this in later chapters, but that is how it works. And it should be 5 volts, but yet it reads 3.5 volts. And that again is because you are introducing a small margin of error when you plug in your cheap meter across that resistor. To continue, we want to find out the resistor 2 voltage drop. ER2 equals current total times resistance total. So the voltage drop at resistor 2 equals 0.00066 amps times 10,000 ohms, which is the ohmage value at your resistor. And that gives you 6.6 volts, which is higher than expected. Should be 5 volts. But yet, using the amperage given by your formula, that gives you 6.6 volts. So there is a margin of
error
there because of the meter that we're using. So if a better meter is used, say a 50,000
K ohms
sensitivity meter, let's see what that gives us. Using example 2-12 on definitions again, how we get effective resistance. Again, we get half of what it would be because of the voltage divider. So a 50 k ohm resistor sensitivity meter is actually 25 k ohms as shown here. So your effective resistance is 15,000 ohms. With the meter connected, the total circuit resistance becomes R effective plus R2 to equal R total. And your resistance total would be 25,000 ohms in this case with the 50k ohm sensitivity meter. And again, using Ohm's law, I'm just using the same exact formulas as last slide and substituting the new value
50k ohms
and working out the formulas from there. So with the new R total of 25,000, divide 10 by 25,000, which is 10 volts, divided 25,000 ohms. That gives me a total current of 0.0004 this time around. So to get the voltage drop at R1, resistor 1, plug in the values. As you can see, we get 6 volts, a little closer to 5 than before, but yet still we are over the mark. Resistor 2 would be, in this case, 4 volts. So we actually went over the mark and the first resistor and under the mark in the second resistor by using a 50k ohm sensitivity meter, apparently too high. So if a better meter is used, let's say 20k ohm sensitivity, using example 2-12 again, going through the same steps. Again, we're using a 20k ohm, so that half of that is 10,000. Half of the resistor value is 5,000. At those, you get 15,000 divided 7,500 ohms. With the meter connected, the total circuit resistance is as shown in the formula. In this case, 17,500 ohms. So using the total resistance and our voltage, which is 10 volts, we divide 10 volts by 17,500 ohms. We get 0.000571 amps. Using the formula for finding the voltage drop across R1, that's resistor 1, we get 4.29 volts at resistor 1. much closer, but not quite. Resistor 2, we get again a bit closer, but not quite 5 volts, 5.71. So to find the perfect resistor sensitivity meter, we must keep looking. Let's say if I buy a better meter, which uses 30k ohms, 30k ohm sensitivity, we have 30k ohm, 15,000, we have R1, 5,000, added 20,000 ohms divided 2, 10,000 ohms for effective resistance. So resistance total, add effective resistance plus resistor number 2, and we get 20,000 ohms for resistance total. We divide 10 volts by 20,000 ohms, which is your resistance total again. We get 0.0005 amps. So the voltage drop across R1 using 0.0005 amps times 10,000 ohms equals exactly 5 volts. No error. You use the same current total, get the same result for the voltage drop across R2 resistor. So we seem to have found the perfect meter at
30,000
ohms of resistive resolution. What is considered the highest harmless current value? That is no more than 5 milliamps or 0.005
amps. What does GFI mean in electrical terms?
It means
Ground fault interrupter.
it is a mechanism that provides protection against excessive fault currents. The way it works is when the coil in this mechanism
Detects
higher than normal
currents.
on the hot wire, it triggers a relay contact to open the circuit and stop the current. What commonly causes the skin resistance of a person to drop to a lower value? Moisture, like sweat or water. What is CPR? It is cardiopulmonary resuscitation, and it requires up-to-date training to perform.